really don't care to spend much time on this first slide. Does anybody need help typing like 2 rooftop 1.4 in calculator? Does anybody at all? Can you do that? Pretty simple. There's a rooftop key. So yeah, not gonna do that. Oh, the laws of exponents. Let the real numbers a and b be bases. Let the real numbers m and n represent exponents. I'm not too wild about using m's and n's, but I use them. Maybe. Oh. Oh, this sucks. So this is going over the laws of exponents here. Let's see here. Let's start off with something easy. I don't really want to use a and b, nor do I want to use m and n. What is anything to the 0th power? 1. If you take a frickin' frowny face and you raise it to the 0th power, what do you still get? You still get 1. Doesn't matter what you take and raise it to the 0th power, it is 1. Let's see other common rules. X to the a raised to the b. Notice those are superscripts up high. Remember what you're allowed to do with those two things? Multiply them together. That's x to the ab. What if you had, actually just use a smiley face. What if you had a smiley face to the a over a smiley face to the b? A minus b. The smiley face can be anything. You understand that, right? I'm always a little hesitant on using x because kids don't make the realization that it can be anything. It's just something. All right, what other rules do we need to talk about? Because there's like 7 of them. How about x to the negative a? 1 over x to the a. Now this one has what we call a converse. If you saw the x to the negative a sitting in the denominator, what are you allowed to do? Move it to the top. Becomes x to the positive a. There's a rule with fractions. 2 fractions, x and y, both raised to the a. What are you allowed to do with that a? It's kind of like the distributive property. You give it to the exponential space of both pieces. What have I got here? 1, 2, 3, 4, 5. This is a pretty important one. And I wrote it wrong from the get-go. X to the a over b. The exponential space is a over b. I remember that one. It's good. That's the bth root of x, and what is done with x? It's raised to the a power. It's actually, when you do a lot of things by hand, it's more common to do it like this. The bth root of x all to the a. Seems like you guys did that lesson on Excel. I think you did. Well, what rule am I missing? Oh, well, yeah, I can't believe I forgot all about that one. Product rule. X to the a times x to the b. What are you allowed to do with a and b? Add them. And there's your 7 exponential rules. And moving on. We're only going to do one graph here. Graph the exponential function 2 raised to the x minus 3 plus 4. The general idea here when to graph these things is to, when you talk about exponential functions, just find the horizontal shift and make a table centered around it. It can be taught through transformations, but then there's a whole lot of transformation rules you got to know. So I would just locate the horizontal shift and make a table centered around that thing. Now you guys have been using notation like this since Algebra 1. You have. You have x plus x minus 3 and then plus 4. What's the minus 3 telling you to do? It's with x. Well, go which way? Go right 3. What's 4 telling you? Up 4. When you actually start doing your graph, you're going to shift the entire thing to the right 3 units. You're going to shift up 4. Now that doesn't mean that this is a point on this graph. It doesn't mean that. Not with exponential functions. It does mean, however, this is basically a center. Just kind of like the origin is kind of a center. This is a center of this graph. So what I would do is I would make a small table centered around 3. And I wouldn't go too far back or too far forward, maybe just back 2 and up 2. But there's your center. Now you have x values, plug them in, and what do you get back? You get y values back. If you plug in that 3, you'd have 2 to the 0th. 2 to the 0th, add 4. You got 4, sorry, 5, right? If you plug in a 2, you'd have 2 to the negative first power. What's 2 to the negative first power? 1 over 2. Add 4, 4.5. If you plug in a 1, you'd have 2 to the negative second. That's 1 over 2 squared, which is, add 4, you got 4.25. Now, if you can't do this in your head, I guess you just punch buttons on a calculator, right? You know how it works? I'm just using the storage feature up here. Storing it over to my brain and plugging it in. That's all I'm doing. If you plug in a 4, what would that exponent be? First power, what's 2 to the first? 2. Add 4, 6. Plug in a 5, I think you got a square going on. 2 squared's 4. Add 4, you got an 8. And there's your little table. That's all you really need. So the right one up 4.25. To the right 3 up 5. To the right 4 up 6. To the right 5 up 8. I forgot about 2, didn't I? About right there. Now this is an exponential function. Exponential functions generally look like this. Sometimes they look like this. Sometimes they look like this. And sometimes they look like this. What we plotted looks like the first thing I drew. It's going to look like that. Now this dashed line here, this vertical shift up, is actually functioning as something to this graph. It's something we talked about last chapter in chapter 5. What is this dashed line functioning as? It ain't vertical. Horizontal. What's your horizontal asymptote? Four is wrong. You can't say 4. It is a friggin' line. Y equals 4. What's the domain of this thing? Negative infinity to positive infinity. It runs forever left, runs forever right. What's the range of this thing? Low y value, what is it? It's really, really close to 4, rises to infinity. Now, I didn't spend a whole lot of time going over it as to will it ever hit 4. But like if you let, I don't know, x be negative 97, you'd have 2 to the negative 100th power, right? That's 1 over 2 to the 100th power. And then you add 4. Are you still above 4? If you have 1 over 2 to the 100th power plus 4, are you still above 4? Can you give me an x value that would make this thing drop below 4? No, because you always got something plus 4, right? The thing has to stay above 4 its entire life. And is there a single exponent that exists that makes a positive number negative? That's right, Savannah, there's not. So the thing always stays above 4 its entire life. It gets really close to it, but it never quite gets it. That's the only graph I'm going to do with you. The number e. That is the definition of the number e. E is the limit as n approaches infinity of 1 plus 1 over n to the n power in calculus. But you're not in calculus, and I'm not going to require you to know that definition. Is there an E button on your calculator? Yeah, there is. You used it last year and the year before that. Some of you. E has a value of really close to 2.72. Usually if anybody ever asks you to do calculations by hand, they will actually tell you to use 2.72. E to the first, 2.72, 2.718 something. Most people tell you to use 2.72 if you're doing something by hand. But it's on that calculator, and I know every one of you punched that button in Algebra 2. So you know where it's at. All right, let's do some actual solving. Solve each exponential equation. What we're going to want to do on problems like these is we're going to try and get these to have a common base. We're going to force a common base. Now, the reason we can force a common base is because if x to the a equals x to the b, what must be true about a and b? They're equal because their bases are the same. We want to force to a common base. And for some kids, it's a little tricky. You know, calculator can calculate, but you got to tell it what to do. And that's what y'all are missing. The small base is usually the hint. Rewrite the other one as a power of the smaller base. Is 32 a power of 5? Sorry, is 32 a power of 2? Yeah. You know, you might have to see how many times 32 enters, or 2 enters that thing, or something like that. But 2 enters 32 how many times? That may not have been the right choice to say. It is kind of 16. 32 divided by 2 is 16. Divided by 2 again. Divided by 2 again. I've divided by 2 how many times? 1, 2, 3. Divided by 2 again. That makes 4. And then divided by 2 again down to 1. It's 5. 32 is 2 to the 5th power. Because I can divide by 2 5 times until I hit 1. So here's what I know. 2 to the 3x minus 1 equals 2 to the 5th power. I sought the common base. I got the common base. Since the bases are now equal, what must be true about the exponential space? They must be equal. So 3x minus 1 must equal 5. Add your 1, you'll get a 6. Divide by 3, what you got? 2. All right, here we got one with E in it. It won't be too bad. Hopefully it won't be too bad. The left-hand side looks good to me. I wouldn't try to manipulate it. The right-hand side needs some manipulation. Think of your rules of exponents. What are you allowed to do with this 4 and negative x? Multiply them, right? Well, that would be, so we'd have 1 over e to the 3x times e to the negative 4x. Now, where do things with negative exponents belong if they're in the numerator? They belong in the denominator. This is kind of a, I'm probably taking too many steps here, but I'm allowed to move it down low. Maybe when I see it down low, I realize that I can vote with the exponential space. Add it. So what's 3x plus 4x? Now, we are really close to having these things be the same, but they're not on the same level, are they? One's numerator, one's denominator. That little theorem I wrote down earlier about x to the a being equal to x to the b, they were on the same exact level. We need to get these things on the same level. We can either shift the left-hand side down low, or we can shift the right-hand side up high. Which one do you want to do? I'd shift the right-hand side up high. Now, if I shift the right-hand side up high, it's no longer e to the positive 7x, it's e to the negative 7x. So what must be true now about the exponential space? It's equal, because the bases are equal. 2x minus 1 must equal negative 7x. You're going to add your 7x and get a 9x. You're going to add 1 to the other side and get a 1. You're going to divide by your 9, and your x value is a 9th. Was that so bad? Look right underneath this one at C. What's your common base going to be? 3, right? 27 is 3 to what power? Cubed. Now what you have to do is you have to write it like this. 3 cubed parentheses 2x. Because you're moving it up through multiplication, right? What's that 3 times that twice x? 6x. So 3 to the 2x minus 4 equals 3 to the 6x, and you should be able to take it from there. You'd say 2x minus 4 equals 6x, and you'd be done with it. 2 steps. The one right below is kind of interesting. If 5 to the negative x equals 3, what does 5 to the 3x have to equal? What I ask myself when I look at problems like this is, what happened to 5 to the negative x to become 5 to the 3x? And the answer is in the exponential space. What do you multiply that negative x by to become a positive 3x? A negative 3, right? The exponential space is multiplied by a negative 3. And that happened on the left. And if it happens on the left, where else does it have to happen? On the right. So what happened is we multiplied the exponential space by a negative 3 on the left, and if we do that on the left, we have to do it on the right. There was already a 1 that was understood to exist there. So 5 to the 3x would be equal to 3 to the negative 3rd power. So 5 to the 3x is equal to 1 over 3 cubed. What is 1 over 3 cubed? 3 times 3 times 3. 27. And that should be it. I think the last thing in there, I think if you flip over, all you got is homework. Those are some word problems. Yeah, you're going to ask me about word problems anyways next time I see you. So no point in talking. We are, aren't you? You are. It's what you do. Because you can't read, because you hooked on buddy. You guys that go to Sunday school and learn how to read Old English, your reading comprehension go way up.